Hi, we are still in quadratic equations. At the end of this video, you should be able to solve quadratic equations with difference of two squares. Let's begin. Look at your given. You have numbers and they seem to have a pattern. What are these numbers? They are actually the perfect squares. They are the result of multiplication of the number to itself. You should be able to list the first 15 squares in 30 seconds. You may need them later on during the work. The perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and so on. And there's more. There are infinite. Next, this is the lesson we learned yesterday. Applying your FOIL, multiply x minus 2 times x plus 2. You have your first, x times x is x squared. Then you have the outer, x times 2 is 2x. Then you have your inner, negative 2 times x is negative 2x. And then your last are negative 2 times 2 is negative 4. When you write them together, you have x squared plus 2x minus 2x minus 4, and then you combine like terms. When you combine like terms, it's actually they're gone. You have only the first and the last result. Notice the middle terms eliminate each other. The result is called difference of two squares because the first term is a square and there's a minus, which is difference, and 4 is a perfect square number. Usually a difference of two squares is a result of multiplying x times x minus a number multiplied to x plus a number, or alternately x plus a number times x minus the number. It always results to difference of two squares pattern. Okay. When you have a difference of two squares, a squared minus b squared, then you could factor it as a minus b multiplied to a plus b, or if you interchange them, a plus b multiplied to a minus b, the order does not matter. They are the same. Going back to your example, meaning to say, if you are going to figure out what terms were multiplied, actually it's x minus 2 times x plus 2. And that's factoring, determining what terms were multiplied to get a given. That's factoring. Now, there are 4 steps for factoring difference of two squares. First, check, are there only two terms? Second, is the first term a perfect square? Third term, is the last term a perfect square? And is there a subtraction between the two numbers? If all of these are true, you can factor using this method. The steps of factoring difference of squares. This chart will help you to determine which type of method to use. First, sometimes it also includes GCF. Number of terms, there might be more than 2. But if you have a difference of two squares, the terms are always going to be 2 terms. This will make sense later in the GCF. Example, you have x squared minus 9. When factoring, you use your factoring table. You have a GCF, no. And then the 4 steps of determining, are the difference of two squares steps true? There are 2 terms, yes. Is the first term perfect square? Of course, yes. Then you can factor it x times x because it results to x squared. And is the second term a perfect square? 9, yes. And it's a result of multiplying 3 times 3. Since it's a perfect square, there should be a subtraction between, yes, and therefore it's not both minus. Remember, it's a pattern. One is plus, the other is a minus, or alternately, minus here and then plus here. It's the same. And that's how you factor a difference of two squares. You factor the first in a separate, and then the second number separate, and then group them together by parentheses, and then have a different signs on each pair. One is plus, the other is minus. Okay, you can have the minus first and then plus here. The order does not matter. Let's have another example. There's no GCF because it's perfect squares. Are the difference of two squares are the given a difference of two squares? Are there two terms? Yes. It's a perfect square. Yes. First term is x times x. The second term is 5 times 5, and then since there's a subtraction between them, so you can have plus and minus, or minus plus, and then that's your answer. That's the factor of x squared minus 25. Okay, next, this one is not a perfect square, so therefore there must have been a GCF. What's the GCF? It's actually 3. But if you factor out from both, you have 3 times x squared and then 3 times 4, and then you factor it out. I mean, you separate it when I say factoring out, so you put it outside the parentheses, then it becomes 3 is multiplied to the blue ones. You see how the unfactored are left inside, and now it's obvious that the x squared minus 4 is a difference of two squares. So we can now factor the difference of two squares. There's two terms. Is the first term perfect square? Yes, x times x. Is the second term a perfect square? Yes, it's 2 times 2. And since it's a minus, then we can proceed the difference of two squares method, 1 plus 1 minus, and therefore that is your answer. And that's how you factor difference of two squares. Sometimes if it's not a perfect square, it means there must have been a GCF, and you have to factor it out to come up with the perfect difference of two square inside the parentheses after factoring out a GCF. You may review this video if you encounter similar to this case. Okay, and that's a review of your factoring of difference of two squares. This is your main lesson. No, not yet. So, pop quiz. What is the factor of x squared minus y squared? Answer in 5 seconds. You have two choices. You have 4 choices. Which of the following is the correct factor? And the correct answer is actually R, 2 and 3. It's not a repeat. It should be alternate. Minus can come first or plus come first. The order doesn't matter. That's how you factor difference of two squares. Okay, and this is your main lesson. We are going to learn to apply difference of two squares in factoring or solving a quadratic equation. When we solve a quadratic equation, we will apply the zero factor property. What is zero factor property? If a and b are real numbers, and if a times b is equal to 0, then we could presume a could be the 0 or b could be the 0. That is, if the product of two numbers is 0, then at least one of the numbers must be 0 to make it equal to 0. Or it could be both of them are 0. It's just a theory. It may be half true, first is true, or the last statement is true. But that's the idea of zero factor property, which we will apply in solving quadratic equations by factoring. And this is actually a general rule that will be applied later on in a factoring a quadratic equation, solving quadratic equation that involves factoring. Okay, let's have example. If you notice, it was the same problem but with equal to 0. So it makes my explanation easier. So when we solve a quadratic equation that involves difference of two square, since this is equal to 0, that makes it a quadratic equation, then we will apply factoring of two squares. Remember, how do you factor? And then we will apply zero factor property afterwards. How do you factor? You have x squared is factorable by x times x, and then your 9 is factorable by 3 times 3. And then since it's a minus here in the middle, it means it's a difference of two squares. Then indeed we can apply your technique of factoring difference of two squares, 1 plus 1 minus, and that's the factor that we need, which we will replace x squared minus 9, because x plus 3 times x minus 3 is a factor of x squared minus 9. And now we have your new factored form of the quadratic equation. If you notice, I turned it into blue because at this time we will now apply your zero factor property. The red part is the factoring part. So according to your zero factor property, to find the roots or the solution, you are going to equate a is equal to 0, b is equal to 0. Therefore, you just separate both factors, x plus 3 is equal to 0 and x minus 3 is equal to 0. That is the idea of zero factor property, and then we can find the solution. So taking off your parentheses, minus 3, you have negative 3. Plus 3, you have x is equal to 3. And it's done. We found the solution. The solution of the problem x squared minus 9 is equal to 0 are negative 3 and positive 3. Why are they solution? If you substitute negative 3 here, negative 3 squared is 9. 9 minus 9 is equal to 0. If you have a positive 3, 3 squared is 9. 9 minus 9 is equal to 0. They are solution because they make the equation true if you substitute them. Unlike to your previous lessons, we learned how to apply graphing method to find the solution. This time we applied factoring method to find solutions. You could actually check your work by graphing, but you make sure you turn 0 into y when you graph, and the graph should be a parabola going up, and it should intersect on negative 3 and positive 3 of x-axis. Okay, let's now proceed to number 2. And guess what? It's going to be familiar. This was actually the problem we solved in the second factoring method, and so we will apply factoring, and then we will apply zero factor property to find the solution. Remember, how did we factor? Since it's a difference of two squares, we factor x into x times x, and then 25 is actually a perfect square. You have 5 times 5, and then you fill it up with plus and minus. You don't repeat them because it's not going to be a difference of two squares. If we multiply it back, it does not give you. We make sure one is plus, the other is minus, and we now have the equation in factored form. And now we will apply your zero factor property. What was the zero factor property? It is saying we can find the solution by separating these factors and equate them both to zeros. So you have minus 5, no, this is plus 5, and then let me fix it. And so now it's fixed. So you have your first root is negative 5, and then the second root is positive 5. And they are our solution. Again, these are the values. When you substitute on x, it will make the equation true. It will become equal to 0. Negative 5 squared is 25. 25 minus 25 is equal to 0. The same works with 5. Okay? And we are now on our last example. And guess what? This was your last problem that involves GCF. This is not a perfect difference of two squares. Why? Because after factoring, we actually factored out 3 to come up with a difference of two squares. Factoring out your 3 and writing it outside the parentheses, you can now have a perfect square, x times x, and then 2 times 2 for 4. And now that's your factored form for your ready for your zero factor property. Since there's only two solutions, then we can just equate your first part 3 times the x plus 2, and then the second part is x minus 2, which will be your b. 3 times x plus 2 is going to be your a part. X minus 2 is going to be your b part. So I multiplied by distributive property, 3 times x, 3x, 3 times 2 is 6. Here you can proceed by adding 2 on both sides and you can find your solutions already. Your solution on the right side is positive 2, but the left side is not yet ready. Minus 6 minus 6, and you get negative 6 here. Divide by 3 both sides and you get your solution negative 2 for your right side. And that's your solutions. The solutions are x is negative 2 and positive 2. Take note again, I did not use the ordered pair. It will make it x and y. You could write it this way, or you could have the previous wherein you have and in between. X minus 2 and x is equal to 2. And that's how you solve quadratic equations with difference of two squares. Sometimes it's not directly a given perfect squares. It could be that you need to apply GCF. The GCF on this one is 3. Factor out 3, and then you have a difference of two squares. Then you can apply and proceed further with your difference of two squares. Your worksheets involve a problem like this. Otherwise, your problem is going to be easy like this. It's directly a difference of two squares. You just factor it directly. X squared is going to be factored as x times x. 25 is 5 times 5, plus and minus, and then write them back. Write it in equation form equal to 0, and then proceed with separating each factor equal to 0, and you can now found your solution. And that's it. It's now your turn to try your worksheet. This will be the GCF problem with GCF involving difference of two squares, but it has GCF. Thank you.